So we've covered the first four laws: Boyle's, Charles' law, Gay-Lussac's, and the combined version of them. Let's go over Dalton's law. It's not in the PowerPoint, I don't think. At constant volume and temperature, the total pressure exerted by a mixture of gases is equal to the sum of the pressures exerted by each gas. So what this states is if you have, for example, let's do 1 liter container, and we have a 1 liter container full of oxygen, and the pressure inside of it is, let's say, 1 atmosphere. And then if we have another 1 liter container full of nitrogen, and its pressure is at half an atmosphere, what Dalton's law states is if we combine these, so that we have oxygen plus nitrogen, so the same two gases in here, and it's still a 1 liter container, we would have 1.5 atmospheres of pressure. So the pressure of both oxygen and nitrogen is the sum of the individual pressures. That's all it says. The pressure exerted by atoms of oxygen hitting the wall plus the pressure caused by nitrogen atoms hitting the wall sum together to give you your total pressure. It makes sense, right? Because we assume that the individual gases are so tiny they don't react with each other. So if you were to just pump in all the nitrogen into the container of oxygen, it's not going to interact the oxygen and the nitrogen aren't going to react with each other. They're not going to interfere with each other. The pressures just sum together. That's Dalton's law. Alright. Let's go over Graham's law. So Graham's law says the rate of fusion and diffusion of two gases, A and B, are inversely proportional to the square roots of their formula masses, meaning their atomic mass or molecular mass. It can be a ratio of molecular speeds of fusion divided by diffusion times distance traveled by molecules or amount of gas diffused. So let me first recap what fusion. So diffusion is just the spreading of gas molecules throughout the container until it's evenly distributed. A fusion is the passing of gas molecules through a tiny opening in the container. So another way of saying that, so if we have a partition separating the gas on one side and a vacuum on the other, if we remove this partition, then the gas molecules are going to spread out by diffusion. If we poke the tiny hole in this partition, what's going to happen is gas molecules will eventually find their way through that hole. It'll take a long time, but they'll eventually pass through that hole and fill the other container. So diffusion is just if you open a can of Coke, the CO2 is going to come out and fill the room. If you have a small hole in your bottle, so if you don't close the lid too tightly, and there's a tiny little crack, eventually the gas is going to escape. That's why you can have, for example, a Coke go flat, a sealed Coke, because there's a just depending on the size of the hole, depends on how long it'll take for it to eventually leak out. So as a whole. So another way of saying Graham's law is the speed A or speed B is equal to the square root of mass B divided by mass A. So when it says rate on your note, that's the speed. This rate could be ratio of molecular speeds times distance traveled by molecules. So as it says on your notes, this rate can be various different things. But I think on your homework, the only thing is speed ratio. So how much faster one is to the other. And what this basically states is if you have so I'm pretty sure what this states is if you have a small little tiny hole, you have some gas A in here. Some of these molecules are going to go through that hole, so I'll call this gas A, and I'll call this gas B. Let me check to make sure this is the right analysis. We'll look that up and see if it means what it is. We won't ever really use Graham's law. Yep. Oh, yep. So I believe what this law means is if we look at the rate at which gas A is going through this. So we're talking about how much these particles move in here, the rate at which gas A flows into the B side, and the rate at which the B side flows back into here. So it's basically the mixing of two gases. It's somewhat important, like if you have a can of helium, you want it to be pure helium. You don't want air to get in, and you don't want helium to leak out. The last law is the ideal gas law. We'll learn more about this later. So let's look at the combined gas law first. So the combined gas law is PV divided by T is equal to some constant. Some constant. What is that constant equal to? So the ideal gas law is written as PV equals nRT. Doing some rearranging, we see that it's PV over T is equal to some nR. From the combined gas law, we know that this is constant. So this is going to be constant. This is, so N is the number of moles. So again, this formula only works if mass is constant. And R is equal to, let me look up better values. Nice. If you look at this table, you can see it. So this is called the gas constant. I think it does. Yeah, gas constant. So R is equal to 8.3145 liters per times kilopascal divided by mole Kelvin. R is also equal to 0.0821 liter times atmosphere divided by mole times Kelvin. And R is also equal to 62.3637 liters times torr. That should be a capital T for torr. Divided by mole Kelvin. What you'll see here is that these are all three just different values for when the pressure is in different units. So if your pressure is in atmospheres, you use this. If your pressure is in kilopascals, you use this. And if your pressure is in torr, or what's another name for torr? Millimeters mercury. So R is equal to 62.3637 liters times millimeters mercury per mole Kelvin. You could use either one of these. Note, if I were to give you, for example, if I were to give you volume in milliliters and pressure in atmospheres, and I told you that R is equal to 8.3145 liters kilopascal per mole Kelvin, what would you have to do? you would have to convert the volume from milliliters into liters, and you would have to convert the pressure atmospheres into kilopascals. So we would have to add in, for example, when plugging it into this equation, you'd have to do some dimensional analysis to make sure the units match. So let me go over the homework real quick, and I'll work out a few more examples. So what is sorry. So a gas is at a pressure of 1 atmosphere and is at 20 degrees Celsius. What would be the final temperature if pressure is increased to 1.5 atmospheres? So a gas is at a pressure of 1 atmosphere and is at 20 degrees Celsius. What would be the final temperature if pressure is increased to 1.5 atmospheres? So remember combined gas law. We can put the initial values on one side and then come over here and write the final versions on the right. If it doesn't talk about a value, so it doesn't talk about volume, we assume it's constant and we can remove volume. And so we have, this is PT or TP, so this would be Gay-Lussac. So this is our initial pressure, P1. This is our initial temperature, T1. This is our final pressure, T2. And so P1 equal 1 atmosphere. T1, it's in Celsius. We have to convert it into Kelvin. So that'd be 293.15 Kelvin. Pressure 2 is 1.5 atmospheres. And we are looking for the final temperature. So P1 over T1 is equal to P2 over T2. We are solving for T2. So multiply both sides by T2. And we have T2 times T1 over T1 is equal to P2. T2, again, we're solving for T2. It's being multiplied by a fraction. So you can multiply both sides by the inverse. T1 and T1 cancel each other out. P1 and P1 cancel each other out. And we get T1 is equal to P2 times T1 over P1. Plug in units. P2 is equal to 1.5 atmospheres times T1, 293.15 Kelvin. divided by pressure 1 is 1 atmosphere. And that's equal to 439.75. Atmospheres canceled out, we're in Kelvin. We can go back to our original unit of Celsius by subtracting 273.15 and get 166.575 degrees Celsius. So just basic algebra, solving for your missing variable. We start with our equation. If it doesn't talk about a variable, we just remove it from it. Identify our variables from the problem. If we have a temperature, convert it into Kelvin. Does that make sense? Simple enough, right? So, Google passed out the homeworks, yes, because I was meant to give you a homework days ago, but everyone was except for like 2 people, I think. And then yesterday we had a lab. Good meeting. I don't think any of these uses the ideal gas law, except for the next homework. For number 7, do chlorine to ethane. So chlorine from the rate of chlorine to the rate of I'll go ahead and tell y'all this. So Graham's formula is rate A over rate B equal to the square root of the mass of B over the square root of the mass of A. That's Graham's formula. Write your answer as the rate of chlorine to the rate of C to ethane. So just put, when you do the square root of mass, you can be the mass of C2H6 divided by the mass of chlorine. Because you can look at the ratio in two different ways. Just make it easier if you wrote it like that. So that was number 7. To give you a hint on number 6, I think I'm sure you'll ask me about it. So what is temperature? What's the definition of temperature? Temperature is average kinetic energy. What is kinetic energy? What's the equation for kinetic energy? This is the only time you'll use this in the whole class. Kinetic energy is what? Do y'all remember? 1/2 times mass times velocity squared. So if temperature is average kinetic energy, and CH4 is moving at 0.098 meters per second squared, its temperature is going to be equal to the average kinetic energy of this gas. And it asks you to solve for the average velocity of carbon dioxide, CO2. If it was at the same temperature, that means it has the same average kinetic energy. Hey, this is number 6. So if they're both at the same temperature, their average kinetic energy has to equal. The 1/2 mass velocity squared of this has to equal the 1/2 mass velocity squared here. That's your hint for that one. Again, it's just algebra. You can use molar mass for the masses of that or atomic mass. Periodic table. Number 11 is also going to be Graham's law. Let's actually work number 11. Bless you. I will first others. That's the code word. So number 11, 1 mole of H2S gas escapes from a container by a fusion in 77 seconds. How long would it take 1 mole of NH3 gas to escape from the same container? Well, which law are we going to use? Which law does this deal with? Which law is used to solve this problem? Definitely not. Yes. You should clearly see that this is grams because we are talking about a fusion. Like literally the only thing here that deals with a fusion is Graham's law. So Graham's law is the rate of a fusion between two gases. So if you read this, the rate of a fusion, and it says right here that this rate can be either the ratio of molecular speeds. It can also be a fusion slash diffusion times. It can also be distance traveled by the molecules or amount of gas diffused. So for rate, you can plug in speed. You can also plug in time. They both work out. So this means let's let A be H2S and B be NH3. So we know that the rate, according to Graham's law, the rate of H2S divided by the rate of NH3 has to equal the square root of the mass of H2S divided by the square root of the mass of NH3. So let's calculate the masses. We have 1 mole. Oh, yes, sorry. See, I'm testing you guys. I flipped it in my head, and then I know I had to flip it, so I flipped it again. So 1 mole of H2S, and we need to convert it into mass, so we need to use molar mass. So I need to convert this into grams. We have a mole on bottom, a gram on top. So I'm going to estimate this. You'll need to do the precise values. I know hydrogen has a mass of 1 roughly, and sulfur has about 28. So this means that H2S, hydrogen sulfide, has about 30 grams per mole, right? So we put 30 and we put 1 mole here. Again, that's just the molar mass. You can get the exact values off the periodic table. So this means that we have our mass is 30 grams for that. So mass of H2S is equal to roughly 30 grams. Yes, y'all will have to do the exact numbers. So NH3, nitrogen is roughly 14. Hydrogen is roughly 1. So that means we have 3 hydrogens, so that'd be 3 plus 14. So NH3 is roughly, 17 grams per mole? So 1 mole of NH3 is equal to about 17 grams. And we know that the rate of H2 we can use time. So rate of H2S is equal to 77 seconds. So basically, rate of H2S divided by rate of NH3 equals square root of mass NH3 divided by the square root of rate of H2S. We're solving for this rate, so I'd multiply it to the right side, and then I would multiply by the inverse. So moving it to the right side, I have rate H2S equal to the square root of mass NH3 over the square root of, I put rate, that should be mass H2S then I can multiply by the inverse, so it's the rate H2S times the square root of mass H2S over square root of mass NH3 is equal to the rate. So our rate was 77 seconds, or square root of NH3. So NH3 is the bottom number. That was 17 grams. And 30 grams for the other one, roughly. And so you should get an answer somewhere around 102.288 seconds. Again, this is approximate because I didn't use the real values. We won't really be using Graham's law anywhere. Gas laws, though, are important to other ones. Again, in this class, I assume you'll all know algebra and can do this. If it makes it any easier, start out with numbers and just do algebra with the numbers to begin with. I personally don't plug numbers in until the very end. Are there any questions? Besides the algebra, should be easy, right? You have your laws, read the question, identify which one. I think I identified all the ones that aren't just the main four gas laws. Yes.